Myself, Dr. Vijaykumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In today's session, we are going to see the problems on correlation and covariance in the random process. So, at the end of this particular session, student will be able to learn two learning outcomes. The learning outcome one is, first we will see the definition of correlation and covariation of random process. In the learning outcome 2, what we will do is, we will apply the concept of correlation and covariance concepts in solving the practical problems. We will recall the formulas of correlation and covariance. So, later on we will see the problem solving session. So, for a random process x of t, the autocorrelation function is mathematically defined as Rx of t1 comma t2 is equal to expectation of x of t1 into x of t2. If the random process is said to be wide and stationary, the conditions to be satisfied are the expectation of the random process must be constant, expectation of x of t must be constant, and autocorrelation function must be a function of time difference, that is Rxx of t comma t plus tau must be equal to Rxx of tau. Okay, these are the two conditions need to be satisfied to verify for a wide and stationary random process. So, and the formula of autocorrelation function is this one. So, we will recall the properties of autocorrelation function. The mean square value of random process x of t can be computed as autocorrelation function at tau is equal to 0 at origin gives you the mean square value, and the maximum value of the autocorrelation function is located at Rxx of tau is equal to 0, and also the autocorrelation function is an even function of tau. Next, the fourth property will be useful in solving the problems. If a random process x of t has non-zero mean value and ergodic with no periodic components, if I want to compute the mean whole square, the formula is limit tau tends to infinity Rxx of t is equal to expectation of x whole square. And one more property, if x of t is periodic, obviously the autocorrelation function is also periodic, and if x of t is ergodic has zero mean. Fourth property, we have non-zero mean, this is having zero mean, because of zero mean it will be equal to 0, and the autocorrelation function of a random process cannot have an arbitrary shape, it will have some fixed shape which will satisfy the properties of autocorrelation, like autocorrelation function is an even function, autocorrelation function will have maximum value at tau is equal to 0. Definitely it will have some specific shape which satisfies the autocorrelation properties. And the next property is, a random process x of t has zero mean and has a DC component a, y of t is equal to a plus x of t, then ryy of tau is equal to a square plus rxx of tau. Two random process is a combination results in a third random process, let us say z of t is equal to x of t plus y of t. If I want to compute the random process of the newly formed random process, the combination of first and 2 is equal to Rz of tau is equal to Rxx of tau, Rxy of tau, Ryy of tau, Ryx of tau. And next we will recall the definition of cross correlation function. Cross correlation function is a measure of similarity between two different random processes. The formula is defined like this, Rxy of tau is equal to expectation of x of t into y of t plus tau. And the properties are pretty much similar to autocorrelation function. Cross correlation function is also an even function of tau, and if you want to compute the cross correlation, this will satisfy this inequality can be used. Absolute value of Rxx of tau is less than or equal to square root of Rxx of 0, Ryy of 0. And one more inequality is, Rxx of tau will be always less than or equal to arithmetic mean of Rxx of 0 and Ryy of 0. Next, if two random processes x of t and y of t are said to be statistically independent and are at least wide and stationary, Rxy of tau is equal to x bar into y bar. If two random processes x of t and y of t have zero mean, then it will be equal to 0. So, let us apply the concept of autocorrelation definition and the properties, and similarly cross correlation definition and properties for solving the practical problems. So, let us see one problem. Compute the variance. So, we know that variance is a statistical parameter. Compute the variance of the random process x of t when autocorrelation function is given to us. If we are able to remember the properties of autocorrelation function, we can compute the statistical parameter variance. We know that variance of x is equal to expectation of x square minus expectation of x whole square. So, this is the mathematical formula. So from the properties of autocorrelation function, I can compute expectation of x whole square using this formula. Limit tau tends to infinity, Rxx of tau gives you expectation of x whole square. So when tau is ranging towards infinity, 2 by 1 plus infinity will be 0. So this value is equal to 16. So which is equal to mean whole square. So the mean value will be square root of 16, mean value is 4. And similarly, one more property is there to compute the mean square value. This is the mean square value. So the mean square value of a random process can be computed using the property of autocorrelation function. When autocorrelation function at tau is equal to 0 gives you the mean square value. So substituting that tau is equal to 0, 16 plus 2 by 1 plus 0, we will get 18. So the mean square value is 18 and the mean value is 4. We will substitute these values in the formula of variance. Expectation of x square is 18, expectation of x whole square is 4 square. So 18 minus 16, we will get the statistical parameter variance value as 2. So with the help of the properties of autocorrelation function, we can compute the statistical parameters mean, mean square value and variance of a random process. Let us see one more practical example related to the properties of autocorrelation function. An autocorrelation function Rxx of tau, this is an autocorrelation function of x of t random process. Another autocorrelation function y of t Ry of tau is given, and given that they are statistically independent and 0 mean random process. That means the random process will have some mean value, it is not 0. And they are statistically independent, Now we need to compute the autocorrelation of the sum x of t plus y of t. So we need to compute w1 of t. So w1 of t autocorrelation function we need to compute. The formula of autocorrelation function is rw11 of t comma t plus tau. So that is expectation of w1 of t into w1 of t plus tau. So w1 of t is x of t plus y of t, w1 of t plus tau is x of t plus tau plus y of t plus tau. So multiplying and splitting the limits, this is the formula we will get. Since given that they are statistically independent means Rxy of tau is equal to Ryx of tau is equal to expectation of x into expectation of xy, is equal to 0. So they are 0. So w1 of t plus tau is Rxx of tau plus Ryy of tau. Rxx of tau is e power absolute value of tau plus Ryy of tau is cos of 2 pi into tau. Next we need to compute the autocorrelation function of x of t minus y of t. In a similar manner, we will apply the formula x of t minus y of t. Here also we apply the condition statistically independent random process. So this will be equal to 0. So Rw22 of t plus tau is Rxx of t plus Ryy of t. Next, the cross correlation function for the third random process is we need to compute the cross correlation between w1 of t and w2 of t. w1 of t and w2 of t are the combinations of x of t and y of t. Now we need to compute the correlation between these two formed newly random process, x of t plus y of t, x of t plus tau minus y of t plus tau, multiplying and splitting Rxx of tau minus Ryy of tau. So since this one and this one will become 0 because both are statistically independent, this will be vanishing, this will be vanishing, only two terms will present Rxx of tau minus Ryy of tau. So this is the cross correlation function for the w1 of t and w2 of t. Next, one more practical problem. For a random process x of t, the mean value is given, the correlation function is given, we need to compute and we need to verify whether it is first order stationary or not. To verify first order stationary, the mean should be constant. Given mean is 6, so clearly it is a constant value, it is first order stationary, it is true. Next, we need to compute the average power, and the average power value is also mentioned as 61 watts. Let us check. Average power is also equal to the mean square value. So the mean square value can be computing by making the autocorrelation function tau is equal to 0. So e power 0, 1, 36 plus 25, 61 watts. So the second statement is also very much true. Next, the third statement, whether the given random process is ergodic or not. So when do we say random process is ergodic? If the time average autocorrelation function and statistical averages are equal, then we can say it is ergodic. Or else from the properties of autocorrelation, if mu x of t is not equal to 0, if x of t is ergodic with no periodic component, this is the formula. Applying this formula, we will get 36, which is equal to mean whole square. So, the condition is satisfied, the statistical averages is equal to the time averages, hence it is ergodic random process. The next condition is we need to verify it is Whiteson stationary or not. For a Whiteson stationary random process, the autocorrelation function must be a function of time difference and the mean should be constant. So, both are satisfied. So, the fifth condition is also satisfied. Next, we need to verify whether it is having periodic components or not. So, it is not having any periodic components, hence the statement is false. Next, we need to compute the AC power of the random process. AC power is also termed as variance. To compute the variance, already we computed the mean square value. We know the mean value. Mean square variance is equal to mean square value minus mean whole square. Mean square value is 61. Mean is 6. 61 minus 6 square, 25 watts. This is the AC power of the random process. Next, we will see the definition of covariance. Covariance is a measure how much two random variables vary together. So, the covariance and the autocorrelation function, correlation function can be related as Cxx is equal to Rxx minus x bar whole square. If you expand this one, we will get this kind of function. So, let us compute the covariance for a given random process. X of t is equal to sin omega t plus phi, where phi is a uniformly distributed random variable. Since the phi is a uniformly distributed random variable, the uniform density function is written here. First, we will compute the correlation. The correlation formula is expectation of x of t into x of t plus tau. So, sin A sin B is written as cos A minus B minus cos A plus B. Again, expectation of this function, what we will get 0, and expectation of constant is 1 by 2 cos omega tau. So, Rxx of tau is 1 by 2 cos omega tau. Next, expectation of x of t, sin integration is cos 2 pi minus cos 0 is 1 minus 1 0. So, the expectation is 0. So, we know the covariance formula Cxx is equal to Rxx minus x bar whole square. Rxx is 1 by 2 cos omega tau, x bar is 0. So, the answer is 1 by 2 cos omega tau. And this is one more problem which is related to the mean and variance of a random variable. Expectation of x of t is given, autocorrelation function is given. Now, we need to compute the mean and the variance for a newly formed random variable which is related using the relation y is equal to integral 0 to t integral t. So, expectation of y, so 0 to 2, 0 integration of 3 is 6. In a similar manner, expectation of y square. So, integration, we will get the autocorrelation function. Doing the integration, we will get 40 plus 4 e square. This is expectation of y square. So, expectation of y we computed. So, the variance is equal to expectation of y square minus expectation of y whole square. We will get 4 into 1 plus e power minus 2. So, we will see the problem related to the covariance. A random process x of t is given sin omega t plus phi. Y is a uniformly distributed random variable over the interval 0 to 2 pi. Covariance we need to compute. So, phi is a, y is a uniformly random variable. So, the density function of uniformly distributed random variable is given. So, the expectation of x of t sin omega t plus y, fy of y is 1 by 2 pi. So, this integration we will get cos 2 pi minus cos 0, what we will get 1 minus 1 0, the expectation is 0. Next, covariance, expectations are zeros. Now, we need to compute, we know that the covariance is equal to Rxx minus x bar whole square. Since this is 0, covariance will be equal to correlation function. Correlation function we need to compute. Expectation of x of t1 into x of t plus sin A sin B written as cos A minus B minus cos A plus B. Again, the expectation of this time difference, this is tau, and this expectation what we will get 0. Expectation of cos will be sin 2 pi minus sin 0 0. This function we will get 1 by 2 cos omega t1 minus t2, which is equal to tau. So, this is the covariance for the given random process. So in this session what we have seen is the learning outcome 1 is we have defined the correlation and different types of correlation, ACF and CCF auto and cross correlations, and we defined the covariance, and also we have solved the practical problems related to the correlation and covariance. So in the next session what we will see is we will see the LTI systems. We will define LTI system and we will see the practical problems related to LTI systems. Thank you.